Okay, so let me just say a couple of words because I just came back from, I was looking at the same monitor, but came from a special event that took place at West Point. They organized a forum that I attended together with Stephen Greenblatt from Harvard University, who is an expert on Shakespeare, a Harvard University professor. The general title of the session, it was aimed at cadets. There were more than 1,000 cadets from West Point attending it. And it was focused on the dialogue between the humanities and the sciences, the fact that there are two cultures that do not connect much. And, it goes back to, decades ago when and also continues now when there is mistrust between the two cultures. And the purpose of this forum was to explain why the two cultures should collaborate, and there is an important input to science that can come from the humanities and vice versa. And humanities have an important role to play in the future of technology and science. And I mentioned towards the end, I hope they will make it available publicly, perhaps on their YouTube channel. But I basically mentioned the Black Hole Initiative as an important forum that brings together philosophers and scientists and plays an important role of demonstrating that the dialogue can exist. And perhaps today's talk will also serve that important purpose. So without further ado, I'll let Fabio introduce our speaker today.
All right, so today it's our pleasure to host Daniel Kennefick. Daniel received his doctorate in physics from the California Institute of Technology, and he was a postdoctoral researcher at Cardiff University in Wales and at the Caltech before joining the faculty at the University of Arkansas. He is the author of books of history of gravitational wave theory and the 1919 Eclipse expedition to test the general relativity. No shadow of doubt is the title of the book. And the co-author on Einstein Encyclopedia. He's a fellow APS, the American Physical Society, and scientific editor of collected papers of Albert Einstein. So without further ado, as Javi was saying, please, Daniel, take it away.
Thank you very much, Fabio. Let me share my screen here. Hopefully you can see my first slide. The title of my talk is The Wagers of Science. You'll see that a bet, the story involves Kip Thorne, who's quite well known for enjoying an occasional wager with fellow scientists. A bet which is of central importance in many ways to the topic that I'll be discussing, which is, I suppose, broadly speaking, the history of numerical relativity, but especially actually looking at certain important aspects of the fairly recent history of numerical relativity. It's not a very old field in any case, but I'll try to sketch a little bit of its early history briefly. But I'm interested in certain questions such as, quite important from the point of view of history, sociology, philosophy of science. What are good models for doing science? Is big science a good idea? Is it good to get people to collaborate, or are people best off working in relatively independently in smaller groups? And how techniques that are useful within a given subject, what Kuhn might have called exemplars, become tested and developed and used and shared and even transferred between neighboring fields, which I think is an important part of the story of numerical relativity. So if I figure out how to advance my slide, then I'll go on. So a great part of the story concerns gravitational waves, because undoubtedly the single biggest influence that numerical relativity has had upon physics is through the study of gravitational waves, especially in the context as in the figure at right is showing gravitational waves emitted from a binary system, but in particular, the biggest influence, and certainly what I'll be talking about today, would be binary black holes. So you have two black holes, presumably they were one stars, though maybe not, but presumably they were one stars. They have spiraled around each other for a long time. They've decayed in their orbit because they emit gravitational waves as they inspiral. And eventually they actually collide. And in the late stages of the inspiral, in the collision and in the merger to a single black hole, they emit characteristic gravitational waves, which can tell us a great deal about these systems, which we really couldn't learn in any other way. Now, gravitational waves themselves have existed as a concept for not much more than a century. Einstein did, however, investigate them in some of his earliest papers on general relativity in 1916 and 1918. And of course, the recent detection of these waves by the LIGO-Virgo collaboration has vindicated Einstein's exposition from that early period, especially the 1918 paper. Nevertheless, there are considerable subtleties in the theory of gravitational waves within general relativity if you try to solve Einstein's equations. And this created doubts about whether they were real, doubts which extended over a number of decades, and doubts which were shared by Einstein himself. I won't go into it, but suffice it to say that while it is certainly true to say that Einstein shared these doubts, and some of those he influenced, such as, for instance, a couple of his assistants, who I'll mention in a moment, nevertheless, it wasn't just Einstein or those close to him, but there were others within the field over time who were somewhat skeptical either of the reality of gravitational waves, or more importantly for our story, whether a binary star system such as a binary black hole would actually emit these gravitational waves. We should at least start off by pointing out that some early types, if you like, I put the word types in quotation marks here because that we don't think of them as types of gravitational waves today, but they were discussed by Einstein in his earliest papers that I mentioned, and they are indeed spurious. They're longitudinal waves. Of course, there are certain non-GR theories of gravity which predict longitudinal waves, but general relativity does not predict them. These early supposedly longitudinal waves were actually simply a coordinate effect of mistaking flat space for a gravitational wave because you're using harmonic coordinates, which sort of make the flat space look wavy. So just to give an example of, a good kind of skepticism, right? When we could say that people were skeptical of the wrong thing and doubting whether binary black holes emitted gravitational waves. But of course, there's a positive aspect to skepticism too. Probably the most famous catchphrase associated with gravitational wave skepticism is Eddington's remark that gravitational waves travel with the speed of thought. But he was talking specifically about these spurious gravitational waves in investigating the question of how rapidly gravitational waves travel. Do they travel at the speed of light? In a 1922 paper called The Propagation of Gravitational Waves, Eddington showed that these so-called longitudinal waves, not surprisingly, given the fact that they're really just flat space, you can try to characterize their velocity, and you quickly realize that by a shift of coordinate, you can make them travel at any arbitrary speed that you like. And so this was the origin of this phrase, that those spurious waves traveled at the speed of thought. You could make them go as fast as you like just by changing your coordinates. So I'll return to that phrase a little bit later. Okay, so I should mention then, since I advertised the fact that some of Einstein's assistants shared his skepticism and indeed were prominent figures in the debates over the reality of gravitational waves in the post-war period, post-Second World War. The two men in question would be Leopold Infeld and Nathan Rosen, both well-known people in the development of general relativity, well-known in their role as collaborators of Einstein. Some of his more important later papers were written in collaboration with them, like the EIH paper in Infeld's case, or Einstein, Podolsky, Rosen, EPR in Rosen's case. So they do seem to be somewhat influenced by their mentor, but they developed their own position, which, as I said, was skeptical. And Infeld in particular argued that the binary black holes or binary neutron stars, I put neutron stars here, that's a little too specific. He would have said any binary star system wouldn't undergo radiation damping due to gravitational waves. And actually Rosen arguably went even further and said that actually the gravitational waves were incapable of carrying energy at all. And so famously, this was a major topic of discussion at the first real international conference devoted to general relativity. And in fact, it's nowadays usually known as GR1, the first in a series of conferences that continues to the present day. It took place at Chapel Hill in North Carolina because it was organized by Cecile and Bryce DeWitt, who I think had just fairly recently taken up their positions at Chapel Hill. And it was a very important conference. I think it's fair to say a seminal conference for the field, and you'll get a sort of a flavor of that just in this talk alone. And at that conference, Felix Pirani, Canadian British physicist, relativist, showed how to understand the way gravitational waves move, propagated and interacted in an invariant way by focusing on the equation of geodesic deviation. And his ideas, and specifically his talk at the conference, inspired Richard Feynman and Hermann Bondi. Probably initially Feynman, because he did so right at the conference, maybe a day or two after Pirani's talk, to propose the famous sticky bead argument, or a thought experiment, if you like, for the existence of gravitational waves, showing that since Pirani had shown how things would be moved about by the gravitational wave, their argument was, well, if you can move things around, then surely just by friction you can extract energy from the wave. So therefore, presumably the wave does carry energy. And so I've chosen to put up here Feynman speaking with Paul Dirac, not at the Chapel Hill conference. I actually don't know of any photographs of the people at that conference, but it was the inspiration for this series of conferences that I mentioned. GR3 took place in Warsaw. The host was Leopold Infeld. And there's a very famous photograph taken at that conference of Feynman and Dirac together. Also, if you are familiar with some of Feynman's writings, especially his more humorous writings, you may know that he didn't much enjoy being at that conference, and he wrote a rather well-known letter home in which he complained about the arguments that were still going on about whether gravitational waves existed, and he felt that they should have all been laid to rest. So he had a certain impatience with this argument. But the truth of the matter is it went on a lot longer than 1962. It was still rumbling on in the 70s under the name the quadrupole formula controversy. So we should prepare ourselves. We're going to start talking about numerical relativity now, but we should be prepared for the fact that it sometimes takes quite a while to settle some of these fundamental questions. And as I'll discuss at the end, I think part of the reason for this may be the length of time it takes to develop the necessary tools for the task. Perhaps if you're a Feynman, that side of it comes relatively easily, but it doesn't seem to have been particularly quick to happen in either of the two cases we're going to be discussing, which is to say the analytical relativists, theorists working in the period from, let's say, the 50s to the 80s, trying to develop their suite of tools, their exemplars, their theoretical art. And then later, almost over the same period, actually, but developing more slowly to begin with, and therefore having periods of debate into the 90s and the 2000s, would be the numerical relativists, and treading what superficially seems similar ground. They're interested in the question of whether or how we can determine what the gravitational waves coming from black hole binaries are, but finding that, of course, they probably needed a different toolbox, or at any rate, that the tools that were useful in one of the boxes had to be adapted somewhat when they were being transferred into the other box, that is to say, the numerical relativity toolbox. Toolkit, right, is the word. There's an important code in numerical relativity called the Einstein toolkit. Okay, so also at Chapel Hill, we can find the origins of numerical relativity. So since that's the origins of modern relativity as a field, certainly right at the beginning, people were thinking in terms of, well, maybe we could solve the Einstein equations numerically. Indeed, if you look at the conference proceedings, this idea that the equations, the Einstein equations, are difficult to solve was certainly already well established. And Feynman alludes to it when he gives advice to the people in the field at the end of the conference and kind of says, well, I know you guys are all thinking that your equations are difficult to solve. And I said, well, don't worry too much about that. And then if you say to me, well, why don't you just solve them? Then he says, well, I can't solve my own equations either. I use approximations and I press on as much as I can. And he says, don't be too shy about, just trying things. And maybe that's something that we can come back to then at the end. So at Chapel Hill, two young relativists who were there, Bryce DeWitt and Charlie Misner, discussed the possibility of solving the Einstein equations on a computer using numerical methods. And as a matter of fact, at least DeWitt had some previous experience with this. He had worked at Lawrence Livermore earlier in the decade and been involved in hydrodynamic simulations and worked with Jim Wilson, who was then newly arrived at Lawrence Livermore also and went on to be a pioneer in hydrodynamic simulations, including binary neutron stars, for instance. Misner also probably was influential in what seems to be generally recognized as being the first paper which simulates a black hole collision. Not really a binary, it's a linear collision. That was produced in 1958, authored by Susan Hahn and Richard Lindquist. Now, Lindquist was, like Misner, a student of Wheeler's, so came from a similar group. They made use of Misner's initial data, which would go on to play a major role in the field. Hahn worked at IBM. She was an applied mathematician and an expert at numerical methods and computing. And she had access, perhaps a key aspect, not the only reason I'm sure that she was involved in, not the only contribution that she made, but importantly, she had access to these rather expensive machines. Apparently, the machine they used was an IBM 7090, actually owned by IBM. This apparently is what the console looked like. So this was a very pioneering effort. The computer, though expensive in its day, apparently nearly $3 million if you wanted to buy one, it was, of course, very slow and not very powerful by modern standards. Usually at this point, one inserts a remark about how one's phone is much more powerful than this computer. And indeed, this was a pioneering effort, but you could argue, I don't know how true this is really in practice, is something hopefully we might learn more about as I go along. I should mention this is all report essentially from a historian's point of view, a work in progress. But you could argue that one of the effects of this was to show, well, maybe the computers really aren't there yet, that they're inadequate to the task at hand. And it maybe was a little bit, there seems to have been a little bit of a gap before the next step, which didn't take place again in the usual version of events until the 1970s, when DeWitt had his students tackle the problem anew. And the most important, he had put several students to work on this matter. The most important of which for our story is Larry Smarr, whose picture is shown here. They produced a number of papers, and Smarr even managed to extract gravitational waves from the black hole collision. So that earlier work, as I mentioned, it simulated two black holes colliding, but it didn't tell you what the waves being produced were by this collision. Because to do that, you would have to have your grid go way out to the far field region. Okay, analytically, you'd say, I want to know what are the waves at infinity. Well, you probably can't fit infinity onto your grid anyway, but maybe you can't even go very far from the grid, in which case you really can't say what gravitational waves are being produced by the collision. So that wasn't done until the 1970s. And we're still dealing with a collision, and we're not, I think, at this stage at full three-dimensional work anyway. So the computers had improved, but an important point to note is access to them was still limited. And I believe that DeWitt and his group depended on DeWitt's association with Jim Wilson at Lawrence Livermore for access to the supercomputers needed to do the calculations at this time. So it's worth mentioning, again, it's a kind of a conventional part of the story of this field, that because there was a lack of access to supercomputers by university researchers, at least in the US, again, one is told that at this time some US researchers would go abroad, for instance, to Germany to find a university which they could collaborate with that had access to a high-performance computer. Smarr submitted to the NSF an unsolicited proposal known as the Black Proposal, because of the cover which is shown here. And this inspired the NSF to create several supercomputing centers, including the National Center for Supercomputing Applications at Urbana-Champaign, which was where Smarr was at this time, I believe. That institute, or that program at Urbana-Champaign, the NCSA, became famous in other ways than numerical relativity, though it has played a very important role in numerical relativity. For instance, it's where one of the first graphical web browsers, NCSA Mosaic, was written. And another thing that I should mention, since I'm talking to the BHI, is visualization. An important challenge that early numerical relativity researchers faced was how to display their work and how to show people what their results were, especially when dealing with three-dimensional simulations. And this led to various creative efforts, and most importantly to the use of video techniques. And that often at considerable expense in the early days, because of course the apparatus wasn't in place to do it. So it was quite a tricky thing to take the output of the computer, to visualize it in some fashion. And this is not a particularly early example, but still one that goes back at least 20 years that I've shown here. I'm very happy that someone who's well known to the BHI, Emily Schoolberg of Cambridge, is working on this issue. And I think it's a very important one, and one that I know very little about, but I feel I should at least flag it here as something that I'm relieved to find that is being investigated. So if we then think about the binary black hole problem as it existed, let's say in the 1990s, so we've, as I say, in a very brief overview, followed the progress of the field up to this point. And this is kind of where I joined the story in a couple of ways. I should mention that I'm not a numerical relativist, so I can't speak with any authority on the subject, although I'm, as I say, trying to grapple with the history of the subject. By the 1990s, it did seem as if the numerical relativists were ready to tackle the problem of black hole binaries, not just collisions, and maybe in full generality, three-dimensional, and most importantly, extract the gravitational waves from such a system. And the timing appeared perfect because the LIGO project had been funded by the NSF basically at the beginning of the decade or the end of the previous decade, and by sort of the mid-90s was in the early stages of construction. And it was pretty clear already at that stage that this would require gravitational templates extracted from these kinds of simulations, because one of the stronger parts of the signal of two black holes in spiraling and merging would be from that merger phase. And it was pretty clear that the considerable body of tools and techniques that had been developed by analytical researchers up to that time just wouldn't be sufficient to give a very correct, accurate, precise template of what the gravitational waves would look like. And that was very important for LIGO, because it was widely expected that in amplitude terms, the signal would most often be quite buried in the noise. And so some sort of optimal filtering where you took advantage of the fact that you had some cycles and you could sort of integrate up over the cycles, but you can only do that if you have an idea of what the signal actually looks like, what you're looking for. And nobody had ever seen these waves before. So the theorists were going to have to provide that, and the analytical theorists didn't seem to be able to do it in this important part of the signal. So in the early to mid 1990s, the NSF encouraged the formation of a Grand Challenge Alliance to tackle the binary black hole problem. This was something that the NSF was interested in doing at the time, the idea that there were certain important topics, especially maybe in the computing area, which were ripe to be tackled, but with big computers, large programs, and it seemed a reasonable bet that given the kind of large number of person hours that might be needed to tackle these kinds of monolithic codes, that the best thing to do was to get these alliances together, a sort of a big science effort. Now, it wasn't going to be practical to bring everybody together and stick them in one place at Los Alamos or something like that. Even the Manhattan Project wasn't really only at one place, but still, you did bring people together. That's not very practical from an expense point of view, if nothing else. So the idea was, well, these groups can work together remotely, and we'll try under the aegis of this NSF program and the specific grant to get them to collaborate together in an effective way. And you can see here that there were quite a number of groups in the United States that were brought under the umbrella of the Grand Challenge Alliance. And they had collaborations with groups in Europe too. So there was a great deal of collaborative effort. And it was, of course, relatively early days for doing just what we're doing now, you know, talking remotely in various ways, including conferencing and so on. So I won't even go reading through the list in the interest of time. Just to give you an idea of my perspective, I was a graduate student in the early 90s. And I do remember that in one of the first group meetings I attended, I was a graduate student of Kip Thorne. Kip came into the room with a large sheaf of papers laying out the work that needed to be done by theorists to assist the LIGO effort, telling us graduate students in his group, you guys have to be prepared to work on this kind of thing. We need to be working in gravitational waves, and we need to be focusing on issues that are relevant to data analysis, so maybe actually data analysis techniques, but also to sources that will be of interest from a LIGO data analysis point of view. And right then and there, of course, he had pointed out that binary black hole mergers would be very important and that they would need to be done by numerical relativity groups. So that wasn't going to be us. that was going to be other groups like the Grand Challenge Alliance. So towards the end of this period, at the end of the decade, I was very interested in history of science as well as relativity. I was very fortunate. I have to mention Kip really at this point, because I can tell you that I said to him, listen, I'd really love to do a little history of science project. And instead of throwing me out of his office, he said, well, you know, you should look back at this quadrupole formula controversy. That was a very interesting historical episode. And that one thing led to another. And before you know it, I had decided I really wanted to follow the development of numerical relativity. And I did quite a lot of interviewing of people at this time. So now this is a kind of an after part of that same project, right? I interviewed people back then at what in hindsight was a pretty interesting period. Maybe it wasn't the most interesting point to interview everybody, but it was the time I did it. Now I'm sort of hoping to go back and get a before and after perspective. So this means that I was present at the final meeting of the Binary Black Hole Grand Challenge Alliance, even though I wasn't a numerical relativist myself. And Kip was there because he was giving a sort of a talk, one of the last talks given to that group, sort of discussing their progress. And during the talk, he proposed a wager. So we've come to the bet, the wager of science. That was the title of the talk. Kip bet that LIGO would see the signal from a merging pair of black holes, a binary black hole, or at least have it in its data. Maybe we wouldn't be able to actually see it because we didn't have a template, but it would be there and to be discovered whenever we had the template ready. That would be there before the numerical relativists had correctly predicted the waveform. Now, of course, you might argue Kip had apparently been talking about such a wager before the meeting, because I know that Larry Smarr mentioned it to me before the meeting took place. Maybe, of course, he was trying to give them the incentive to press ahead. I can tell you that there was considerable reluctance in the room to take the bet. I know I've talked to some people since who said they personally felt fine about it. I'm sure that must have been true. There was quite a large group of numerical relativists in the room. It wasn't called the Grand Challenge Alliance for nothing. I have to say, I thought many of them did not look totally confident. And you did hear people say, what are the odds? What's the spread? So they did take the bet. I mean, I certainly felt that they were honor bound to do so. But I have the feeling that they weren't very keen. And of course, the situation at that time was that no simulation of a three-dimensional binary black hole had ever run for even one complete orbit. In most cases, they didn't even get close to that. So there were various challenges, and I'm not a numerical relativist, and I'm not yet at the stage where I can give you a very detailed analysis, I'm afraid. But nevertheless, give an idea of the kinds of issues that were being faced at this time. So an example would be black hole excision. Obviously, the trouble about the singularity at the center of the black hole is that's not going to be good for your computer. And even the most casual science fiction fan knows that your computer will freeze or explode or something if it's asked to deal with an infinite number. So a singularity is not, or not a number, a singularity is not a good place to ask your computer to look at. But there are various things that you might do. I mean, as an example, you might decide to take advantage of the fact that in principle, nothing can escape from inside the event horizon of the black hole. And so the computational grid doesn't even have to go all the way down to the center to where the singularity is. You just don't have to go far in beyond the horizon, because in principle, anything in there that you don't want to deal with can't get out anyway. The trouble is, of course, that while nothing can escape from inside the event horizon unless it can travel faster than the speed of light, which physical things can't, numerical error, of course, by definition, doesn't obey the Einstein equations, and it can travel at any speed. So we return here to Eddington. All right. Numerical error, it turns out, can travel at the speed of thought, and the speed of thought of a supercomputer is very fast indeed, especially by the time we're talking. Maybe Hahn and Lindquist computer at IBM. Incidentally, that IBM computer that we looked at earlier was an early example of a transistorized computer. The earlier models of that computer had vacuum tubes, and that was one of the early ones to similar architecture, but they had transistorized it. So that was pretty early going. Now we're up to much faster computers, if not quite to the speeds we have today. And the trouble is, yeah, your errors can pile up even faster if you have a very fast computer. So errors can propagate across the grid and crash your code. And so excision turned out to be quite a challenge. And one of the examples of the later breakthrough that we'll talk about in a moment was the idea of using a puncture to take out a bit of your grid, which was just kind of, in many ways, it's kind of a simple rough and ready idea. And as an interesting example of how you never know where the breakthrough is coming from, people were so nervous about these punctures. I've heard people, so far I've interviewed people now looking back, and they can remember people saying at the time we're speaking of now, around the year 2000, between the end of the Grand Challenge Alliance, let's say 2000, and the breakthrough year, which was 2005, people saying things like, well, I don't know what the eventual code that will solve this problem will look like, but I can tell you it won't have punctures in it. But it turned out that, that those codes typically did have punctures in them. There was so much nervousness about this particular approach that the idea was that you shouldn't ever move the puncture around on the grid. And so you should just try to move everything else and keep the puncture where the singularity was stationary. And then it turned out that moving punctures actually were the way to go. And I've even heard the story that I have to stress. I have no idea how true this is at this juncture. I'm hoping that I will, one of the questions I will answer, that it was almost serendipitous, you know, that in one of the groups involved, they had a switch in their code to make the punctures, you know, be stationary and not move, because they felt that's the way you should run it, and that somebody inadvertently ran it without the switch on, and so they got moving punctures and it ran fine. Now, of course, one has to be a little bit dubious about these kinds of stories, but these stories do at least alert us to the role that serendipity may play in the history of the field such as this, especially in the early history. So it's something that we should at least be alive to the possibilities of. So I just advertised the breakthrough, and in 2005, Franz Pretorius, well, I think he had just stopped being a Caltech postdoc and moved on to Princeton maybe, so I'm not even totally sure that when the paper was published, I don't think he was still a Caltech postdoc. But at any rate, the point I'm making here of a young researcher, essentially working alone, at least his paper is a single authored paper, was able to evolve a black hole binary through an entire orbit and the merger and I believe even the ring down, and was followed shortly after by other groups 6 months later in the same calendar year at UT Brownsville, University of Texas at Brownsville, and NASA Goddard. And since then, numerical relativists have gone on to make a number of remarkable discoveries about black hole mergers that I won't even talk about because we're going to try to focus on this breakthrough. So an interesting question then is that it seems to me just jumps right off the page at one, is, you know, small science versus big science, which is bigger, right? We have the NSF trying to fit the field into this idea of large collaborations in the 90s. And I think it would be fair to say that many people viewed the Grand Challenge Alliance as a failure. Now, I'll argue in a minute that again could be wrong as well, right? But at any rate, that was certainly something that was commonly said. And then, sure enough, as if to drive home the lesson, you have the fact that the very first breakthrough paper, it's single authored. It's not even a small group, it's an individual. So was the whole Grand Challenge idea misguided? Was the NSF trying to propose a model that really didn't suit the field at this time? Now, one take from an important figure in the field, Larry Smarr, at the time, I'm talking about an interview with him made towards the end of the Grand Challenge Alliance, was that the creation of tools was a necessary step for success in numerical relativity. He said that the analytical people have had decades to develop their tools, but we haven't had that here. And so he felt that the Grand Challenge Alliance was useful in helping to develop these tools. And it would be fair to say that code such as Cactus, which was being worked on at least partly within the Grand Challenge Alliance at that time, and certainly within a fairly collaborative framework, have given birth to things like the Einstein toolkit, which are still very much in use today. And you could certainly argue that that they would be a positive legacy of the Alliance. And people did talk at the time about collaborational infrastructure. Obviously, there are some advantages to being the sole author of a code. I mean, anybody, even myself, who's a very janky programmer, you know, knows it's very comforting often if you feel like you're the only person who's ever going to run this code. You don't have to worry too much about, you know, proper procedures and documentation and all that. But on the other hand, if the code is going to be used over a long period of time by multiple people, that increases the amount of effort and work. And so a large code probably most of the time does require many person hours, even if it is one person There is therefore the need for something like a collaborational infrastructure, which is a term that I heard people like Ed Seidel, who's now the director of NCSA, or at least was very recently, to describe codes like Cactus, which use things like thorns, which are a kind of a plug-in to allow people to use parts of the code but bring in their own bits. And these were conscious efforts to enable collaboration between groups at different times as people move around between groups. There was a problem that was expressed to me quite a bit at the time, that because these codes were often so monolithic and only the people who wrote them really understood them, that there was a danger that people got stuck in postdocs for a long time because you couldn't let them leave the group because they wrote the code. Another aspect that may be relevant in terms of what's the right approach to take as a model for collaboration. We just talked there about the idea, well, maybe it is helpful to have an alliance to develop this collaborational infrastructure. But another aspect is that you do come across people talking about a real scattergun approach at this time, especially in this period, perhaps from 2000 to 2005, where it seemed almost that the field was in a fairly random mode. You just had to try things. And remember, if we go back to Chapel Hill and the analytical people in their early days, Feynman was really arguing for that. Right? Just try things, guys. You just don't be too worried about rigor. He was really sort of arguing against mathematical rigor. He said, don't worry if it looks like it's a crappy idea. Give it a try and see if it works. And certainly, I've heard people say things like that some programmers were actually using a random number generator to try to decide amongst the parameters they had available, which one should they let be free parameters. And you know what, let's just have a random number generator and just try a bunch of things just to see what will work. And of course, I mentioned the allegation that serendipity played a big role in the success of the puncture approach, the moving puncture approach to black hole excision. So you could argue then, if a scattergun approach is actually the way to go in certain instances, then of course maybe that is a reason why only when they let the field go its own way, a sort of a free market approach to science, just letting everybody try things, as many things as possible, and see how you get on. But of course it still could be that the toolkit is very important, right? Because maybe just trying things there needs to be a certain amount of direction and also a certain ability to pick up other people's techniques. And again, collaborational infrastructure may be important. To give another example, and the last one, of a specific technical issue, boundary conditions. Historically, the problem that analytical theorists faced, they also went through, I mentioned this period of skepticism in the analytical side back in the 50s, 60s, and into the 70s, in fact. They were trying to show that binary systems did radiate gravitational waves, did or did not radiate gravitational waves. One of the big problems they had is they thought, okay, I could do a calculation, but they got, especially in the early days, in the 50s and into the early 60s, they actually got different results and that didn't agree with each other. So some people were doing the calculation wrong. And often enough, it seems likely that the issue may have been failure to impose correct boundary conditions. You'd like some kind of no incoming wave boundary conditions. Some people got results, for instance, that their binary star system was gaining energy. Well, how can it gain energy if it's emitting gravitational waves? Well, of course, if you don't have the right boundary conditions, you may inadvertently be introducing incoming gravitational waves, which carry energy to the system. So now the question becomes, how do you correctly impose the boundary conditions? And one answer, it turned out, was they weren't even totally sure about which infinity they were supposed to use. But luckily in the 60s, along came Roger Penrose with his compactified space-time diagrams, showing that, in fact, infinity is a little more structurally subtle and complex than we had anticipated. You've got time-like infinity, space-like infinity. We've got then null infinity, which is where you would want to impose your scry, where you would want to impose your boundary conditions in this case. So this is an example of the kind of tools or the sort of development of the theoretical art that enables you to get over these problems, because you can do the calculation in a more unambiguous way, and you can critique other people's problems in a more unambiguous way. And another example of bringing things in from another field would be, okay, now you know where to impose your boundary conditions, but actually it turns out you have different parts of your calculation for different regions of your space-time. And so the idea of matched asymptotic expansion was brought in by a graduate student at Caltech called Bill Burke, who borrowed it from people working in fluid dynamics and hydrodynamics. And this proved to be another useful tool that was an important advance. So this idea of Techne, development of exemplar, what Kuhn would call exemplars, or a theoretical art is another term that maybe we could use, I think is an important one, and I feel like it's going to play an important role in this area. I sometimes use the term theoreticians regress to talk about what can happen before you have a sufficiently well-developed toolkit at your disposal. You're doing calculations, but it's very difficult to compare the calculations. And if they don't agree on their results, you're almost at a loss to decide how to choose between the different calculations. As the toolkit that's available becomes better defined and the set of exemplars that are at hand become more understood, it is much easier to actually decide, you know what, I think this one is right and this one is wrong for these specific reasons. So you could argue that the lack of progress that was in either field, the analytical and numerical relativity, was a lack of tools or a lack of sufficient development of tools. And one obvious thing then, and this is my last point, would be, was it possible to just transfer the tools or the exemplars from the analytic field into the numerical field? And it turns out that that's not straightforward, perhaps not very surprisingly. Tools often do need to be modified when they're turned to a new use. And how you modify them and the correct modifications may not be particularly obvious or transparent. So even if, and it's not just a matter of transferring tools over, but even if that's what you're doing, it actually turns out that a good deal of practical experience, a good deal of trial and error maybe, is necessary to develop your Techne to the point at which you are in a position to be successful with these new tools. And again, certainly if we look at this period from 2000 to 2005, numerical relativists did spend a fair bit of time consulting analytical people, especially on things like the initial data problem. So an example of this would be if you look at Pretorius's work, and I'm no expert, I have to stress, but one aspect of something that he did do was, again, looking at spatial infinity, he used a kind of a compactified approach. And so this was something that since Penrose had been very common on the analytical side. But I've spoken to some of the analytical people who said that they were consulted by numerical people at this time and said, well, why don't you try using compactified approach to spatial and space-time to spatial infinity? And, you know, they said, well, they looked at me like I was totally naive and said, oh, no, that's not going to be a good idea, because you're losing resolution, they felt, at the, you know, at the very far distant reaches of space-time. And this is important because even with compactification, you still don't have infinity in your grid. So there is a boundary, and you can get reflection of waves. And so we're back at that issue that had confounded the analytical people decades earlier of waves reflecting inward, bringing energy back into your system and giving you a very unphysical result. And it does indeed seem that Pretorius's compactified approach actually did have intense reflected waves coming back in. And so what did he do to get rid of these? Well, he just used numerical dissipation. He artificially introduced dissipation to get rid of these incoming waves. So you can regard this as a hack, right? In computing language, there's a good word for it. They have a word for it, the numerical people. And so sometimes when you're trying to get tools to work, and maybe even when transferring tools, these hacks are necessary. And of course, a hack may appear to be a hack at first and turn out to be just a technique, or it may turn out that it really is a hack and you can do it in a more sophisticated way. You develop the tool. But again, and certainly I've seen people say that one of the things they felt was refreshing about Pretorius's approach was that, you know, he was willing to give it a go. Right. So this again goes back to Feynman's thing, you know, of what might be viewed as, you know, giving it a go, giving it a try. And incidentally, that does, however, leave you with the problem. Back in 2005, even during the breakthrough, the issue was, how do we know which of these hacks, which of these tools, which of these techniques are the ones that are key? And that's not easy to tell. Even today, it may not be easy to tell. Remember, these large codes are somewhat like black boxes, and it can be very difficult to critique them and to try to draw lessons from them. So there are lessons from a historical, sociological point of view, but what are they? Again, it's not so easy for us either. Was the large alliance useful in sharing ideas, allowing larger programs to be developed and used in a collaborative way? Or on the other hand, would it have been better to allow smaller groups to just try things and be more fluid? Are there lessons that funders could draw in this story, right? Was the Grand Challenge Alliance, to take a specific example, a mistake? Or maybe it was, in hindsight, we should regard it as an essential step. It's very, very difficult to know. Personally, I don't yet have an idea. I'd love to feel like I could get to that, but I'm certainly not there yet. Obviously, to finish the story, the theorists, the numerical relativity people ended up winning their bet, right? And famously, I hope this doesn't need too much elaboration so that I can just stop talking and we can go on to questions. Famously, this image, this figure shows the GW 1509-14 gravitational wave signal with the numerical relativity derived waveform superimposed on it. You can see this brilliant match. So they won their bet, and the theorists were able to be there at the moment, contra to Kip's warnings. Although it's fair to say that even though they had a 50-year head start over the experimenters, they were fortunate. It turned out they needed all of the 50 years that it took the experimenters to detect gravitational waves so that they could actually stay not ahead, right? Just reach the finish line at the same time, more or less. So that's all I had to say. Thank you very much.
Thank you, Daniel, for this very interesting talk. And we have some time for questions. Peter.
Thank you. That was great, Dan. I really enjoyed the talk, and I think it's a really interesting episode in the history of theory to try to grasp. I have a question. My question is this. There's a certain way in which DeWitt and others from who had some experience at Los Alamos would come to apply these methods in the way they did. The thermonuclear weapons had required numerical methods from the get-go, and it was not only with von Neumann and Ulam and the Monte Carlo methods, and then Metropolis who puts it on the computer, and it's every time they got a new computer at Los Alamos, Teller wanted to try again to build a so-called classical a thermonuclear weapon of the kind that's never actually been built. But I was wondering if there's a way of understanding why Pretorius came to the methods that he did, given his trajectory. In other words, what helps us make sense historically of those methods that he applied, of the compactification, of the numerical absorption, and all the other things that he was doing? Do you have a sense of why then, there, and him?
Thank you, Peter. Yeah, that is an excellent question. And I have to confess, I don't feel at this stage that I have an answer to that, though it's certainly a question I'd love to be able to answer sometime, hopefully not too far in the future. And it is a tricky business because even if we look back at DeWitt, you mentioned DeWitt, and to the extent that he was influenced, clearly heavily influenced by the particulars of the numerical tradition within the bomb making community. And yet he has written a short paper about this for a festschrift for Jim Wilson. And even there, it's interesting because one gets the impression that what he describes happening is that he worked with a programmer, an unnamed programmer, at least in that paper, at Lawrence Livermore, who obviously was part of that bomb, it seems pretty clear, part of that bomb making tradition. And it does seem as if that, what's tricky about it is it doesn't seem as if, to judge from the account, that DeWitt had much of a hand in the programming. He would provide steps, he would provide the numerical algorithm, and the programmer did the programming. And they did meet, and so there clearly was an exchange of information. And it's a pretty good instance. It would be nice to know more. I'm not at the stage yet where I know more, so I'm afraid I can't say anything more than this. But it does seem a little bit like it's an interesting case because they really had to translate for each other. So I think, to put it into your language, it definitely seems like an interesting case of a need for translation between different disciplines.
You see that too with Bill Press and Tucholsky developing the black hole bomb, I mean, Bill Press was in the midst of weapons things. And, you know, I think that there are ways of thinking that come out of Los Alamos that shape branches of physics. You know, you couldn't do bubble chamber, weak neutral current, bubble chamber physics in the 70s without the neutron transport codes that they got out of Los Alamos. I mean, there's a lot that comes out of that, of those efforts in many branches, some completely unexpected in handling information. And of course, okay. Well, thank you.
Yes.
Again, I think it was a terrific talk.
Well, thank you very much, Peter, and thank you for your question, which I'm really interested in. And let me add one more thing. Yes, I think the bit about Press and Tucholsky is really fascinating. Actually, something that I think I'll look into a bit more. You know, I'm not a numerical relativist, but I've certainly used Press Tucholsky methods. So, but to go back to Pretorius, and again, I don't have a definitive answer there, but I do have the feeling that it is another example of, and at this point it's nothing more than instinct or speculation, that it is an example, again, of translation, to use your term, but maybe primarily coming from a more, you know, analytic theoretic tradition and a willingness to just import those tools and try them. Because I do have this sense from talking to some of the people involved that there was a reluctance, for instance, to try these compactified approaches because it was felt like, oh, numerically, that's not really a good idea. And so somehow or another, he decided to just give it a go. And then, yeah, I see the problem. I see now I'm getting problems here, but I'll just use this hack to get over that. And so again, although I don't know of, to answer your specific question, of all of his influences, I am very interested in this question of, was it a case of just taking things in from the analytic tradition within relativity and not worrying too much about importing things?
Achilles.
Yeah, hi. Thanks for a very nice talk. So I'm wondering, so you know, this slide tells us that the theorists won the bet. When would you say that this actually happened? So obviously by this time where the two are overlaid, we know that, you know, the theorists won the bet. But say, you know, sometime before, did LIGO, you know, while it was in this observing run collecting data, did they have any, you know, any backups as to, you know, if the theorists were wrong, what was there a plan, or was it long known that the theorists won the bet and now we should just compare to?
Yes, that's an excellent question. Yes, I think that to some extent they did work on backups. I mean, they were trying to push analytic techniques as far as they would go. And there are methods like effective one body, which is an example of something that some analytical theorists were saying, well, we can do it this way. But it probably would be fair to say that I don't know that there was anybody in the analytical community who was saying, oh, well, it'll be no problem at all if the numerical people fail because we've got it in hand. I mean, even with effective one body, I think it was very valuable to have the numerical results as part of the process. Keep in mind, of course, that it was always kind of understood that it was highly likely that, you know, numerical methods, you know, using the supercomputers, even with supercomputer speed, it can be slow. You probably can't do every template that way. And so it was always felt like there would be a need for a marriage of different methods. But nevertheless, once the breakthrough was made in 2005, obviously that was a full decade before the, I think it was advantage to have that full decade, and it was needed. And I suppose a good question, I'm hoping to interview Kip later this afternoon as it happens, so I will put for you to him the question, well, when for you was the bet won by the other side? I know that he has agreed that they won it, but you know, at what point? And there was a certain point at which the numerical codes had developed to the point where there was a partly Caltech-based collaboration which was producing the templates for the LIGO template bank. So that would have been an obvious moment, which did take place a few years before the actual detection. So I think there certainly was several years in which everybody would have been pretty happy that, yes, the bet has been won now. And it's just a matter of waiting for the instrument to succeed.
Avi.
Yeah, so there is a broader issue that I wanted to ask you about. I mean, you provide a very interesting, insightful example of, but the bigger question is, nowadays a lot of science is done in huge groups. You can see that in CERN, you can see that many other contexts, and when young people become scientists, they become a drop in the ocean, so to speak. It's sort of like being in business, in the business world, where the agenda is set higher up, and they just, play the role of soldiers in a big army. And so my question to you is, do you still think that there is an essential and important role for individuals in the face of this phenomenon of a lot of social engineering in science, where people are put as troopers in big armies, and if so, how can we encourage that more, so that there would be more Pretorius like scientists that make breakthroughs? Even when we put a lot of funds in the direction of big groups, it's quite possible that the big groups are heading the wrong way because they they took the wrong turn in the highway.
Yeah, that's a great question, and I would be very pleased if I felt I could address that question as a result of the study. And as I say, at this stage, I don't know that I can give you a very definitive answer, but I think at least it's very clear that there are some pretty persuasive bits of evidence in this particular history that it is important to maintain some freedom for individual researchers and small groups to go their own way, just for the reasons that you outline. I mean, obviously, almost anybody would have to accept that regardless of the advantages that there may or may not be in having a large group or a large collaboration that's very well funded and has plenty of resources available to it, obviously, if they do happen to be going in the wrong direction, then probably all of those resources are going to go to waste. So there's something to be said for having other people who are at least resourced to the extent that they can make progress in their own way. And it is pretty clear, I think, from this story. I feel I would be surprised at this point if I change my mind as I go forward on this score, at least, that there was a definite period of up to a decade in length at least, where it just wasn't very clear what was the correct method. And, probably in that context, if that is the situation that you find yourself in, maybe it's not typical of science in general, or maybe it is, I don't know. In that situation, there's probably something to be said for trying different things. And in that case, probably having individuals who are doing their own thing and plowing their own furrow is probably a good idea. Now, you could argue that, the well-resourced groups can, of course, still be useful because they provide a space in which these individuals can be developed, right? So they will have backing and resources at their disposal, and they will have people to talk to. Probably it's not necessarily the best thing that they be totally isolated. But it's certainly, I suspect that many of the people in the field came away with the feeling, whether it's right or wrong, I'm not totally 100% prepared to say, that the Grand Challenge Alliance might have been an example of trying to force things in a direction of big science to suit the funder, when perhaps it wasn't quite the correct way to go. But we should be careful, obviously, to acknowledge that collaborations between groups in different places still plays a pretty considerable role in the field. So it may be that, of course, a balance is needed between larger groups, smaller groups, and even individuals, all in a position to move their own research programs forward.
Thank you.
There is a last question from Gary.
Just an adjunct to Avi's point, and I wonder how much the role of, in this case, computer technology factors in. In the 70s and 80s, it was necessary to join large groups who had access to supercomputers. Today, you may have enough compute power on your desk to do it yourself. Is that a fair characterization of perhaps a change in the sociology of how at least gravitational wave calculations are done?
I'm sure that it is a factor, and certainly even within the field, a part of the lore is that access to machines, did and must have played a pretty significant result. So for instance, in the early days, it was necessary to have contacts within the computer industry itself or at a national lab, because otherwise you probably didn't actually have the access to a computer that could even notionally attempt the task. And as you say, later on, there were better computers, but at the same time, access to them was still, it was better, but it was still pretty restrictive. And obviously, there's the famous story that, and this was sort of within the gravitational wave community. I think it was Gaurav Khanna who first had the idea you could use PS3s and link them up to make a parallel computer of considerable power. So yes, I think it's fair to say that with time, the barrier for entry into the field became lower, and that probably made it more possible to have more groups. So obviously the same is probably, I guess Avi mentioned this in his original comment about big science, because we usually think of that as being big instruments in the experimental sense. And obviously, I mean, that's an issue in this field too, right? I mean, there are only 3 operating gravitational wave detectors that have detected anything so far. So that side of things, you have a big LIGO scientific collaboration, you have a big LIGO Virgo collaboration, and it's only gradually that people are becoming independent of that collaborational framework into which arguably the funders are trying to funnel people, because only those instruments are available. And so by analogy, and as you point out, there must have been an earlier period within the field of numerical relativity when the number of computers, the number of machines that you could run on was pretty limited. And so at some level, you would have to be in a group with access to such a machine to make any progress.
Thanks.
All right, so there's no more time for question, and let's thank Daniel again for a wonderful talk.
Thank you for having me.
Yeah, we'll see you next week. Thank you.